Let's dive straight into this explainer. When we picture cancer, we usually just think of a single lump or tumor, right? And sure, a primary tumor is incredibly dangerous, but a lot of the time it can actually be removed by surgery. The real threat, the reason cancer is such an absolute powerhouse of a disease, is when it learns to travel. We call this process metastasis. Today, we're going to look at that primary tumor like it's a sort of mothership, and we'll treat its deadly spread through the body exactly like a criminal mastermind pulling off a massive bank heist.
Here is our heist blueprint. We'll be mapping out 5 crucial steps today: local invasion, intravasation, circulation, extravasation, and colonization.
Now, to make this incredibly complex biological journey a bit easier to grasp, we can compare the cancer process directly to a bank robber's escape plan across a busy city. Local invasion? That's breaking out of the bank vault. Intravasation is jumping into the getaway car. Circulation is the high-speed chase through city traffic. Extravasation is crashing that car into a new building. And finally, colonization is setting up a brand new criminal headquarters. It's a brilliant, albeit terrifying process.
All right, let's kick things off with step 1, the breakout, or local invasion.
To actually pull off this breakout, the cancer cell has to physically dig through the security walls of its home environment, which we call the extracellular matrix. Now, under normal circumstances, your cells are stuck tightly together, kind of like bricks in a well-mortared wall. They use these proteins called cadherins, which act just like molecular Velcro. But cancer cells, they essentially turn off the genes for these cadherins. They lose their glue, becoming super loose, slippery, and completely ready to start their escape.
But once they're unhooked, the cells are still trapped in a tissue mesh. So what do? They release special enzymes called MMPs. Think of these as molecular scissors that literally snip and cut right through that tissue mesh. With the path all cleared out, the cancer cell uses these tiny leg-like structures called invadipodia to physically crawl away into nearby healthy tissue. And just like that, the breakout is successful.
Moving right along to step 2, the getaway, or intravasation. At this point, the cell needs to travel long distances. That means it's time to jump into the getaway car, which, in the human body, is either the bloodstream or the lymphatic system. Now, our blood vessels are lined with a thin layer of cells called the endothelium. Just like a burglar cutting a hole in a chain-link fence to reach the freeway, the cancer cell sends out chemical signals that actually make these vessel walls leaky. The cell then squeezes through those tiny new gaps, slipping right inside the vessel. And here is where things get really dangerous. Once it's in, it becomes what we call a circulating tumor cell, or CTC.
Which brings us to step 3, the high-speed chase, or circulation.
Look, getting onto the freeway is just the beginning. The bloodstream is a brutally hostile environment for a rogue cell. The blood flow creates massive physical stress and shear force that can easily tear a cell apart. Plus, you've got white blood cells acting like aggressive police cruisers, actively patrolling the blood and ready to destroy literally any invaders they find. So to avoid physical destruction and those immune attacks, cancer cells use brilliant disguises. They'll actually wrap themselves up in platelets, the cells your blood uses to clot. This acts like an invisibility cloak, hiding them from the immune system while buffering them from getting smashed against the vessel walls. Sometimes they'll even clump together with other cancer cells for safety, or, wildly enough, ride inside immune cells like a Trojan horse.
But here is the crucial point. This high-speed chase is incredibly deadly. Despite all of those clever tricks, the physical forces and immune attacks are just overwhelming. Less than 0.1% of these circulating tumor cells actually survive the journey through the bloodstream.
For those incredibly few survivors, the next move is step 4, a new target, known as extravasation.
So the survivor has to crash the getaway car and break into a distant organ to hide. But this brings up a really fascinating mystery in oncology. When they crash, it isn't just random. Think about it. Why does prostate cancer usually spread to the bones? Why does colon cancer almost always target the liver, while breast cancer might go to the lungs or the brain? Well, the answer lies in something called organ tropism, and it was beautifully explained all the way back in 1889 by a doctor named Stephen Paget. He proposed the seed and soil hypothesis. He basically realized that a seed can't grow in just any dirt, right? It needs the exact right environment, the perfect soil, to actually take root.
So our seed, this traveling cancer cell, is actively looking for soil that offers a mechanical trap, like a narrow capillary bed, but also specific chemical welcome signals. Certain organs release chemicals called chemokines. If the cancer cell has the matching receptors for those chemicals, it sticks to the vessel wall of that specific organ, pushes its way right through the endothelium, and finally exits the bloodstream.
And that leads us to the final phase, Step 5, colonizing new soil, or colonization. You see, just exiting the vessel isn't enough. To form a dangerous new metastasis, the cell has to set up a new criminal headquarters and start growing in this foreign tissue. And to grow larger than the size of a tiny pinhead, the cancer cell absolutely needs food. So it literally hijacks the local infrastructure. It does this by sending out signals, like a protein called VEGF, to trigger a process called angiogenesis. This actually recruits and grows brand new blood vessels that plug directly into the tumor to feed the growing colony.
But here is one of the absolute most terrifying aspects of this entire process. Sometimes the new host organ suppresses these invading cells, forcing them into a dormant sleep. These cells can hide away asleep in a distant organ for months or even decades before the conditions are just right and they finally wake up. This is exactly why cancer can unexpectedly recur long after a primary tumor was successfully removed. When you step back and look at the sheer biological odds here, it is just staggering. A primary tumor might release 10,000 cells a day into the bloodstream, but only 1 in 10,000 cells successfully completes this entire heist to start a new colony.
Let's transition over to stopping the spree.
Because even a tiny success rate leads to secondary tumors over time, metastasis is the ultimate challenge in cancer medicine. It's incredibly difficult to treat because it's a massive numbers game. The cells that survive this epic journey have mutated to become highly aggressive and often resistant to standard chemo. Because some are dormant and not actively dividing, traditional chemotherapy, which strictly targets dividing cells, just passes right by them. And while surgery can remove one big primary tumor, you simply can't cut out hundreds of tiny, mutated, dormant metastases hiding scattered across the lungs, bones, and liver.
But the good news is, modern medicine is fighting back by trying to block these specific escape routes. We've developed drugs that try to inhibit those MMP molecular scissors, so the cells literally can't break out. We use anti-angiogenesis drugs, like bevacizumab, to cut off their ability to grow new blood vessels, essentially starving the new colony. We even use drugs like bisphosphonates to block the specific homing signals that draw cancer to the bone in the first place.
Which leaves us with this final thought today. Understanding this extraordinary journey shows us exactly how cunning and adaptable this enemy really is. If a single cell can pull off an almost impossible biological heist, sneaking past security, surviving a high-speed chase, and building a brand new base in hostile territory, what new, ingenious traps must we invent to finally outsmart them? That is the most critical puzzle in modern medicine, and it's one we are getting closer to solving every single day.